Yeah.
So people all right? Homework going okay? So I'll begin by just a few reminders of things which are due over the next few days. So just one reminder today, the WebWork 3 is due this afternoon at 5 p.m. Looks like so far people have been doing the WebWork pretty well on time. It's been good. The written assignment 1 is due next Monday. So hopefully people have had a chance to look a little bit at that. I'd like to make some comments about it toward the end of today. Maybe take 10, 20 minutes at the end to sort of discuss some of the questions which I think might need more attention than others. So I'll make sure, and well, I mean, if I don't stop myself, then someone needs to stop me, I think, toward the end. So those are the major announcements. I think next week we'll have a slightly different meeting pattern, because Monday we will not meet because of the July 4th holiday on Sunday. So there's no class meeting on Monday. So which is why the written assignment is due on Tuesday rather than on Monday. So just remember in the back of your head, forget what I said earlier, the written assignment 1 due on Tuesday of next week at 5 p.m. because we're not meeting at all on Monday. And so I guess, look at the written assignment over, over the next few days, over the weekend, think about questions that you might have. Don't wait until Tuesday to let me know what those questions are, because, I probably won't be able to respond sensibly. And I guess next week I'll have the same pattern. So starting on Tuesday, we'll talk about some stuff. There'll be a WebWork assignment due on Wednesday afternoon. We'll talk about some stuff on Wednesday. There'll be a WebWork assignment due on Thursday, and then probably a shorter written assignment, because we won't cover as much material next week, I think, as we did this week. If you have the book, next week we're going to get the next couple of weeks, we're going to get into a discussion of something called vector spaces. We're going to motivate the construction of a lot of vector subspaces using some facts about matrices that we're trying to develop this week. So if you want to read ahead, that's kind of where we're headed. I'll begin to put some slides and exercises up. I think, I have the WebWork exercises already, so I might just post those late tomorrow, maybe. The slides I think I have to type up and check, so I'll need to do that maybe over the weekend. So you should check back on Monday to kind of see what those look like. Questions about any of this so far? Okay. So the last topics for this week have to do with different sorts of matrix factorizations. We will probably have time to cover 2 out of the 3 posted sets of slides. Depends on how things go. The first thing we're going to talk about is called Ldu factorization. The letters L, D, and U have a particular meaning. L stands for lower triangular, D stands for diagonal, and U stands for upper triangular. So what's being proposed is that if you have a matrix, and I think we'll only, in this section, consider the non-singular case because of some time constraints. We'll worry about some other cases next week, or the week after. Basically, if you have a matrix that has, and again, just a square matrix, I think, for the sake of the conversation. If you have a square matrix which has all non-zero pivots, that's called a non-singular matrix. It's possible in many cases to write down something called the Ldu factorization. LD and U are sort of special matrices, and we'll sort of see maybe why you would want to do that toward the end of that set of slides. There's one thing about Ldu factorization which is a bit weird. The process of building such a factorization depends on having the pivots appear in the right order. So you will remember yesterday we talked occasionally about what would occur if you were sort of doing this elimination process and you wound up getting a 0 pivot, but the pivot below, but you could swap a row in order to replace the 0 with a non-zero number to create a non-zero pivot in the right spot. The thing about it is that that type of thing actually totally destroys this factorization algorithm. So the type of examples we're going to be dealing with, at least at first, are ones in which these types of row switches, we're not really going to worry about something like that occurring. If that does occur, it turns out that you can switch the rows in advance and then conduct the Ldu factorization. You just sort of have to keep track of the different row operations that you're undertaking to kind of remember what rows have to switch. So with that in mind, I think we'll probably just get to the slides, talk a little about the factorization, some properties that it has. So there's slide 1, sort of the introduction. So here we are, 2. Get this way right here. So in this section, we'll begin to look at a major factorization theorem for non-singular square matrices. We only want to look at those. Since the matrix of coefficients will be non-singular and square, we're looking at a model of a system of equations which has a unique solution. So by this point in the class, you probably kind of know what all these words mean. If you've played around with systems of equations, you're probably aware, that the number of pivots has something to do, the number of non-zero pivots, the number of non-zero rows, in fact, has something to do with the quote-unquote size of the solution space. So in some examples that you've done, you wind up with an entire 0 row. In a case like that, you wind up somehow with an infinite number of solutions. If you wind up with a bunch of rows which are not 0, if you can actually completely reduce the thing and you have a non-zero pivot everywhere, you're going to wind up having a unique solution. That's the situation that we want to discuss today. So the theorem is basically equivalent to Gaussian elimination. And so, plus some weird substitutions. So we'll talk a little about what that means toward the end. When I talk about Gaussian elimination here, I'm not talking about Gauss-Jordan elimination. So the sort of thing that people might have done on the web work yesterday, where they take a problem and they totally reduce it to the reduced row echelon form, we're not really going to be doing that right now. When you talk about Gaussian elimination, all you're really talking about is a process which identifies the non-zero pivots. You're not reducing those pivots to 1. So the only elementary matrices which are involved in the factorization that we will produce are the ones which combine rows as linear combinations, the E matrices they were called yesterday. We'll restrict our field of vision to the 3x3 case. We can write some things down in that case. We're not going to really worry about situations where we have to swap rows around either. That will mess up what we want. So I'd like to just start with a 3x3 example. So we'll start by looking at the following system of equations. So you see you have 3 of these equations right here. The system of equations is not homogeneous. If you remember the web work assignment that was due yesterday, you can convert that system of equations that looks like this into something that looks like this. This is called the matrix form of the system of equations. All you're really doing is you're considering the 3x3 matrix right here, coming from the coefficients of the u, v, and the w. You put your indeterminants in a column, and then you have the solution vector right here, -2, -1, and 6. So this guy right there, the thing that I'm pointing that arrow at, is called the matrix form of the system. For the next few slides, we're only going to consider the coefficient matrix. We're going to develop a factorization for the coefficient matrix called the Ldu Factorization. So that's sort of the goal of today. Before I move on, does anyone have any questions about what we're discussing right now? Is this okay?
You said it's basically, well, on a slide, it's basically Gaussian elimination plus back substitution. What did it kind of, I don't know, what does it refer to when you say back substitution?
It means that, so what it means is with the factorization that we get, the first thing we'll do is we'll wind up getting something called the Lu factorization. So Ldu factorization stands for lower triangular, upper triangular. So what's going to happen is we're going to take the matrix A that we start with, and we are going to factor it into a matrix L and a matrix U. And when you talk about substitution, back substitution and forward substitution, what we're going to see toward the end, it just amounts to solving 2 very simple matrix, very simple systems of equations. So basically, when you talk about breaking the matrix up, it's really just going to be, basically what we're going to do is we're going to take the system of equations that we start with. When we factor A into L times U, the effect of doing that from the practical point of view is going to be taking our system of equations and splitting it into two systems of equations, which we then can easily solve. And in fact, this is kind of how a computer wants to do this rather than a human. So that's what's meant by it. So with substitution, we'll sort of see this at the end.
Okay, thank you.
Okay. So the next slide, so that's A, right? So all I did is I just wrote down this slide just tells you a little bit about what I'm calling things. I'm going to let A denote the matrix. I'll let B, the vector, denote the solution vector. I'll let X denote the space of indeterminates, the set of indeterminates. We can denote our matrix equation as AX equal to B. So this type of thing is probably familiar to you from some of the online homework because you've done some of these things already. Often you're working in a situation where the vector B is 0 when you're dealing with homogeneous systems. That's not quite what this is, but it's pretty close. The next point is important. One way of approaching this problem, I mean, whenever you write anything down like this, it looks so much like a linear equation. The temptation to cancel the A is almost overwhelming. It turns out that will occur in the next set of slides when you divide by A, right? You get a solution for X that involves producing a formula for the inverse. It's not quite what we're going to do right now. Instead, what we're going to do is we're going to factor A as a product of lower and upper triangular matrices and then quickly solve two systems of equations which involve these matrices. Cancellation of A will work out in the next set of slides. So when you see something like that in the back of your mind, when you see some equation that looks like this one toward the top right here, in the back of the mind, I think you're probably thinking of something that looks like 2x equal to 3. You just divide by 2. That's actually a pretty coherent way of thinking about what we're trying to do with that notation. But you just have to come up with what 1 over A looks like. So that's the next set of slides, but we will talk about that. So the LU or the LDU factorization corresponds to Gaussian elimination. We'll only use the elementary matrices Eij to do this. So in our particular work that we're about to do, matrices D or the permutation matrices will never really appear. So that's sort of the content, I guess, of the next few slides. So we'll focus on the matrix A first. I first want to be able to produce a formula for A as a product of a lower triangular matrix times an upper triangular matrix. So if this process that we're talking about is supposed to be like Gaussian elimination, then I'll sort of treat it that way. If we wanted to carry out the elimination algorithm, we would first produce a 0 in the 2-1 position, and then we would produce a 0 in the 3-1 position. Now from yesterday, you might remember that this amounts to multiplying the matrix A on the left by the product E31 times E21. Again, what's a little weird about this type of factorization is that you tend to write the product from right to left. I mean, you're proceeding in order, but you're writing stuff to the left, but that's okay. That just is how this type of notation, this type of multiplication actually works. So E31 times E21 times A is supposed to look something like this. So that's probably not surprising. You can convince yourself of that by, of course, minimally, working out what the elementary row operations are, which lead to this type of reduced matrix A. So in this case, this matrix A that we're dealing with is already upper triangular, and that's kind of the goal of the exercise. When you multiply, or when you're carrying out Gaussian elimination as opposed to Gauss-Jordan elimination, Gaussian elimination only involves producing an upper triangular matrix in the place of A. So it involves simply producing an equivalent upper triangular matrix through elementary row operations. And in this example, only 2 elementary row operations are actually needed, simply because the matrix is not so bad to deal with. The first one is that you want to produce the 0 in E21 in the 2-1 position and the E31 position. The equivalent row operations, I guess I probably just will write them over here. E21 is the same as is R2 plus, let's see, I have to remember what the matrix actually was to start with. Right. -1, I guess, right? It's on page 4. R2 plus negative R1 goes into R2. That's E21, and E31 is the same as R3 plus, so let's go back and see it, negative 3, I guess, right? Negative 3 R1 goes into R3. So those are those, we would write, if we're confined to, using elementary row operations, we'd probably record those matrices this way. But notice that, doing these two things is equivalent. The advantage, I think, of using the elementary matrices, at least in this context, is that it is very helpful to produce, it's very helpful to produce a formula for a factorization for A. That's where we're going. So before we move on, does anyone have any questions about where we're at right now? All that's really happened in this case is I've taken the matrix A, I've left multiplied by a couple of elementary matrices in a particular order for the purpose of row reducing the matrix according to the Gauss-Jordan algorithm. If you think about it for a minute, more interesting things can happen with A sometimes. We happen to be lucky in the sense that if you take a look at the second pivot that we generate, it is already the case that there's a 0 below the second pivot, and because of this fact, there's no reason to multiply by an additional elementary matrix. So if you're dealing with a 3x3 case, if you only want to carry out Gauss-Jordan, or rather, if you only want to carry out Gaussian elimination, you're only using the elementary matrices which combine rows. And so if you're only carrying out that algorithm, the most number of matrices that you would expect to multiply A by, if you just want to produce an upper triangular matrix, is 3, because there are basically 2 pivots which will have a position below them. The last pivot, the 1 in the 3, 3 position, there's really nothing to do there. By the time you get there, if that's not 0, then you already have the upper triangular matrix. So is this okay so far? Okay. So one major point that I would like to make, it says we already know that the elementary matrices have inverses. I'm not sure that we totally know it. I'd like to give you the formula for the inverses and maybe talk for a minute about what an inverse is in the context of this set of slides. An inverse, so I'll write down here, and we'll talk more about this in just a second in the next set of slides. An inverse is a matrix, an inverse, I guess, of A, where A is square, is a matrix B for which AB equals the identity matrix and BA is equal to the identity matrix as well. So for our elementary matrices, if you have, usually you denote the inverse with the symbol A to the -1. So, you don't write 1 over A. Sometimes, you might think that might be helpful, but maybe that's too weird. But you need to call it something. So, you usually just call it that. And what that slide is saying is that our elementary matrices all have inverses. And in a sense, maybe that's not so surprising, because if you think about what an elementary matrix is really supposed to be doing, it's supposed to be combining rows in some other matrix. If you want to create a 0 in a certain position under a pivot, you multiply on the left, but you can always unmultiply. You can always put back in that 0 position what was originally there by re-adding the first, by re-adding the row in which the pivot is in. So, so I guess if you go back to slide 6. If you go back to this, if you look at the row operation which produces the 0 right there, originally there was a 1 there. We could always put that 1 back there by taking that row 2 and adding the first row to it. So that's the operation that undoes E21. Does that make sense? So if you have a 0 there, you can always put back what was originally there. And that's supposed to be, and that action is supposed to say, basically represent the inverse of the elementary matrix, which is putting the 0 there. There's an inverse row operation, if that makes sense. Is this okay? So with these matrices, so with these row operations, what you take away, you can always put back. And so they're always invertible. And so that's sort of the principle, that's the principle that we're using. So I want to write down the formulas for those, but again, they're probably not too surprising if you're following along with the conversation. You know, there's an inverse, 6, 7. So here are the inverse matrices. So E21 inverse, it has a 1 right there. That 1 means that you are putting the 1 back into the second row. E31 inverse in this case has a 3 right there. That means that you're putting the 3 back into the third row where it originally was. But there's one thing that we should probably check, and I'd like people to actually take a moment to do this verification. Take this matrix right here, the E21 inverse, and multiply it by E21. So basically, the formula for E21 I probably didn't give, but you probably remember what it is in context. I guess I'll write it down right here. So E21 in this case, the thing that removes the 1 looks like this. So I just want to do one verification, not both, because usually 1 is enough to convince people that what we're doing is reasonable. That's E21, that's E21 inverse. So take a moment and just multiply or take the product of these two matrices to notice that what you wind up with is the identity matrix. Again, just as a review, the identity matrix is a matrix with 1s along the diagonal. We might pause for a moment to think about why it's called that. So right now it's about 923. It should probably not take more than about 3 minutes to multiply the matrices out to kind of see what you get. If you take the inverse of E21 multiplied on the left, multiplying on the left by the inverse of E21, you should get the identity matrix out of that product. Check to make sure that you do. So I'll stop the recording. All right, so we're back. Did people get the identity matrix out of the calculation? Is it good? Good or bad? So when you multiply them, you got the 1s along the diagonal, right?
Yeah, I get
Yeah,
it.
that's
Yeah, so before we move on, one thing that I would like to say, again, I'll go back to the screen. If it isn't clear yet, the identity matrix I is like the number 1. So if you take any matrix A, again, imagine that it's at least square for what we're talking about, then if you either left or right multiply by the identity matrix, you get A back. So you want to think about the identity matrix. If you think about the space of matrices, if you think about the goal of what we're doing, to be like trying to understand matrices just like we understand numbers, thinking about what the 0 matrix is, thinking about how you factor matrices. All this seems like a lot of arithmetic where you're trying to understand numbers, and it kind of is. The role of the identity matrix, when you're talking about matrix multiplication, is that when you multiply the identity matrix times something, you get that same something back. The ones along the diagonal, sort of entail that will be the case. You can always check this through various calculations, but that's the importance of it in the context of discussing matrix inversion. So basically, if you have a matrix, when you multiply a matrix on the left by something like by its inverse matrix, and you get the identity matrix, This is like when you have a number like 2 and you multiply it by 1/2 to get the number 1. So that's the analogy. That's sort of its importance. So back to back to where we were at. So I think that was slide 7. So basically in this situation, you've more or less identified the fact that E31 and E21 both have inverse matrices. And it turns out that those inverse matrices are themselves elementary matrices. So basically E21 inverse has a 1 there, and the 1 that you see there corresponds to the row operation of adding the first and the second row together and replacing the first row with the sum. So, and something similar is true for E31 with the 3 down here. So when you're talking about the inverse matrices, another point I would like to make is that if you think about E21 and E31, they are examples of lower triangular matrices. The non-zero entries, if there are any at all, are below the diagonal and the 0 entries are above. The inverse matrices have the same property. They are also lower triangular. In fact, not only that, they are also elementary matrices. So if you view the set of elementary matrices, if you imagine for a moment how all of these E gadgets work, both elementary matrices and the inverses of the inverse of elementary matrices are in the same set. So you don't have to go outside the set of this type of elementary matrix to find the inverse. They're all in the same place that you might look. So, those are going to be, I think, important points later when we start talking about, the factorization. So you check this. What mileage do you get out of it? One thing that's interesting. Where are we at? Here. Okay. So one thing that's interesting here is what happens when you calculate the product of these two elementary matrices. If you calculate the product in this order, it may not be so totally clear why you would do that, but it has to do with this right here. So I guess I should say something about that. What does U mean in the context of this equation? U means upper triangular. So I think I've been using that. I should probably just use this, like right down here. This matrix that and I think I probably mentioned this earlier, but the matrix that you have right here is upper triangular. We're going to call that U. When we're looking at this particular line right here, our equation that looks like this is the same as this equation right here. So how do you go from here to here? I think I'll do it in a couple of steps. You need to use associativity, but if you have E31, E21A, and that's equal to U, if you multiply on the left by the inverse of E31, so we multiply the equation on the left, we cancel it by E31 inverse. And so we get E31 inverse acting or multiplied by E31, E21A equal to E31 inverse A. So this is a whole lot like solving equations. So hopefully that's what you're thinking about right now. Since matrix multiplication is associative, the left-hand side of this equation is the same as E31 inverse times E31. All of that times E21A, so things associate, and you get E31 inverse A right here. By design, E31 inverse will cancel E31, so the product of these two matrices is I. So this is the same as I times E21A. It's inverse A. But remember, the identity matrix, when it's multiplied by anything, it's like the number 1. It does not change that thing. And because of that fact, the left-hand side of this equation is E21A, and we've canceled one of the terms on the left. And similarly, so I won't do this part because it gets tedious after a while, A is equal to E21 inverse times E31 inverse A by the same reasoning. So, you know, if we were to stop right there, we basically had used these elementary matrices that we discussed yesterday to develop a factorization for a certain matrix A. This matrix A happens to have a full set of pivots. That's pretty important. We didn't have to manipulate the pivots in any way to get rid of zero pivots or anything like that. So that's also a nice feature of A. And in fact, we were luckier even than that, because if we take a look at the second pivot of A, there was really nothing to do there. So there wasn't a third elementary matrix to multiply on the left by to eliminate the last position, I guess, in the 3-2 position in the 3x3 matrix. So what we wind up with is a factorization for A. I'd like to pause for a moment for questions. There's one more thing to discuss here, but before I do it, does anyone have any questions about what we're doing? The goal is to try to produce a factorization of A as a product of a lower triangular matrix and an upper triangular matrix. There's sort of a computational reason to do this, which we'll see in just a second. But that's the goal. We're trying to write down a factorization of A in much the same way that we take any kind of natural number like 9 or something like this. And we try to write down a factorization of 9 in terms of some elementary elements. We call those prime numbers in the natural numbers. But in the language of matrices, we'll probably talk about elementary matrices, at least right now. So does everyone understand the nature of the conversation? Just trying to figure out what A is. We're trying to break A down into more elementary pieces. That's the goal right now. Is this okay?
Professor, could I see the slide again? Could I see the slides, the notes again about the, I just don't know why the E31 multiply the E31, E21 and A is equal to E31 multiply the A. I just
The last slide?
Yeah.
This one?
Oh yeah. I just don't understand the first step. I
Right
just
here?
confused. Yeah.
Okay. So what I'd like to, so here's a way to try to understand like the logic of what we're trying to do.
Mm-hmm.
So suppose you had an equation. Not necessarily an equation of matrices, but just a normal equation of numbers.
Mm-hmm.
So you had 3x equal to 7 in a standard equation. In this situation, how would you solve for x?
Just x equal to 7/3, right?
That's what it would be. But when you do that, what does it really mean to write down x equal to 7/3? Maybe the way to think about it is that you would take that equation and you would multiply both sides of that equation by 1/3. Yes?
Yeah.
So this equation right here is equivalent to the equation 1/3 times 3x equal to 1/3 times 7, right?
Yeah.
And then, if you're really being, super careful about it, you combine the 1/3 and the 3. And of course, you usually, I'll go ahead and leave that as 1/3 by 7 times 7 for the sake of the analogy. 1/3 times 3 is 1, right?
Mm-hmm.
And so this equation right here is 1 times x equal to 1/3 times 7. But 1 times x is just x.
Mm-hmm. Yeah.
Right?
Yeah.
Now, when you're looking over here at what we're trying to do, maybe one of the best ways of thinking about the idea of an inverse is to think by analogy. What you're trying to do with an inverse is you're trying to have something. So I guess if I'm trying to continue the analogy over here, E31 inverse is like 1 over E31. So you're canceling you're canceling the E3, 1, if that makes sense. You're dividing out by it. And so just like in the equation 3x equal to 7, the goal is to get rid of the 3 because you're trying to isolate the 7. You're trying to write down what 7, or you're trying to isolate the x. You're trying to write down what x is, in terms of some numbers. And so in order to see what x is exactly, you can cancel the 3. But the way that most people are going to do this is they're effectively going to multiply both sides of the equation by the inverse of 3. Do you follow that?
Yeah.
So
I'm just the first step. Then I still am confused why the E3 1 multiply the the E2 1 and multiply the A is equal to A. Why the E3 1 multiply the E2 1 is equal to 1? That's mean, yeah, like yeah, just the first step. Yeah, I no
so right here. Your question is about this equation?
yeah. It's equal to U, not but in the equation you said that it's equal to
right. No, you're right. U.
Yeah, I just confused about this.
Is that better? Yeah, right. So yeah, right. And so A is equal to a product of elementary matrices times U. So that helps, right? So you wind up with a factorization for A, right? And what we're hoping to see out of that factorization is that we wind up factoring A into a lower triangular matrix times an upper triangular matrix. Now we haven't talked about the lower triangular matrix just yet, but we will in just a second. So are there any other questions about this? That's the goal. So maybe we're at a point where we can maybe see the end of the exercise. So right here, yeah. So one thing to check. So remember that we have from that thing I was writing, we have A equal to E2, 1 inverse, E3, 1 inverse U. But these are just symbols. You're basically dealing with actual matrices that we have formulas for, so to speak. We can check that E2, 1 inverse times E3, 1 inverse. The product of these two guys is actually this matrix right here. Should take a moment to check that. I think this is a point where I'll probably leave that part to you. Maybe take a few minutes to do this. Remember that E3, 1 inverse and E3 and E2, 1 inverse, they appear on slide 7. So maybe I think right now is about 9:43. Take about 3 minutes to multiply those matrices. What you're trying to verify is that the product of those two inverse matrices is actually a lower triangular matrix. So I'll turn off the video right now. I'll go back to share the screen to indicate the problem that we're looking at. Maybe take 3 minutes to carry out the matrix multiplication. All right, so now we're back. So with that product, hopefully you see that the product of matrices is lower triangular. We can maybe go back to the slides. So what we wind up with is a lower triangular matrix. We'll call it L. And so you factored A. So basically A is a lower triangular matrix times an upper triangular matrix. This guy's lower triangular, notice, because the zeros are up here. We already have a formula for U. U's formula indicates that it's an upper triangular matrix. One natural question is, what do we actually do with this? This part I think I'll probably move through pretty quickly. So this set of slides sort of talks about what you might do with this. I kind of want to move through this quickly because it's probably a little bit less important than talking about inverses. So our vector equation looks like L U X equal to B. That's because this was originally A. Because matrix multiplication is associative, this equation and this equation are the same equation. You just move the parentheses around a little bit. I need a piece of notation. That's why I introduced the C here. You're basically trying to solve two sets of equations in this problem. Remember that you're dealing with things L, U, and B, which are actual vectors. You're trying to do two things in the problem. The first thing you're trying to do is you're trying to find a vector C so that LC is equal to B. That will be solved first, and then finally you're trying to solve the X that will generate that C. If you do that, you will actually solve the system of equations in two steps, and it's essentially because of this right here. I don't want to actually do an example of this right now, so I think I'll probably just move forward. One more thing that I'd like to talk about before I end the discussion on this type of factorization. There is a certain asymmetry to the Lu factorization. So in the example that we're dealing with, what you should notice is that this is the L and this is the U. The L matrix has ones along the diagonal, and the reason why that's occurring is because the L matrix comes from a product of elementary matrices which have ones along the diagonal and are lower triangular. The U matrix is not quite like L in the sense that its diagonal does not consist of ones. So the diagonal of the U matrix has the pivots that you're usually dealing with on it. Remember, this is the sort of slightly row reduced version of A that we sort of started with. So L has ones along the diagonal, U doesn't. If you wanted to have a situation where L and U were somewhat symmetric, you can sort of remedy this by playing around with the matrix U a little bit. I guess what I would say here is that these two guys, these represents column operations. And so it turns out when you take these two matrices and multiply the matrix U in order on the right, you will eliminate, you will basically be able to factor U as a diagonal matrix times some other matrix, which we will confusingly call U. So why do the column operations look like this? If you take U, what you want to be able to do is to eliminate 1 and 1. So the negative 1 that you see here, the purpose this serves is to add together the first and the second column of U and replace the second column with that sum. If you look at this column operation, it's denoted as 1, 3. The goal is to eliminate that 1 right here. And in order to do that, we want to be able to add the first column to the negative of the last column and replace the last column with that sum. And it turns out that these two matrices, when you multiply U by them on the right, will do that. So in the end, what you get a matrix which looks a bit like this. So U times C12, C13 is D. Column operations are reasonable. D is equal to this diagonal matrix. It's a diagonal matrix which contains all the pivots. It turns out, just like with the elementary row operations, matrices C12 and C13 are invertible. And so you can write down a formula for U by inverting this equation on the right. So if you have this equation right here, I probably won't say as much about this. This particular equation, if you multiply on the right first by C13 inverse and then by C12 inverse, you get something that looks like U. And C13 inverse and C12 inverse is also upper triangular. One thing I should write here is what the formulas for the inverses actually are, but they probably aren't that surprising because they just reverse the column operation. So you can check that C12 inverse is 1, 0, 0, 1, 1, 0, 0, 0, 1. You can check that C13 inverse is equal to 1, 0, 0, 0, 1, 0, 1, 0, 1. And so it's sort of the column version of the E matrices that we discussed earlier. And so it's probably worthwhile to take a moment to check. You know, people have already done a lot of matrix multiplication today. We can check to see that the product of these two matrices is upper triangular. This product is equal to a new matrix, which confusingly we'll also call U. And so what we have, you know, after we've done all this, is we've taken the matrix A and we've written it as a lower triangular matrix D times the diagonal matrix times an upper triangular matrix. These matrices all have special properties. Both L and U have ones along the diagonal. And that's what people call the Ldu factorization of the matrix. Basically, Ldu, again, it's taking a matrix. We can get to Lu factorization simply by thinking about Gaussian elimination. To figure out that you can break up the U into a diagonal matrix times another upper triangular matrix, you would generally do or use something called column operations to do this. It's funny because column operations are completely reasonable, but most people build theories of linear algebra around row operations, you know, mainly because it's got something to do with solving systems of equations, so it tends to be more natural. The key thing about L and U in the LDU factorization is that the matrix L is lower triangular with unit diagonal. D, of course, is a diagonal matrix, and the matrix U is upper triangular with also ones along the diagonal. Are there any questions about this so far? So there's a problem on the written assignment where you have a 2x2 matrix and you want to come up with its LDU factorization. I forget exactly which one it is, but when you're working on that particular problem, this set of slides basically provides a way of doing that. What you're going to want to do to produce that factorization is just use Gaussian elimination to, you know, you only have to do one thing, I think, with that matrix because it's got a non-zero pivot. But you know, you want to keep track of the elementary matrix, which basically eliminates, you know, the non-zero values above and below pivots. If you want the LDU factorization, I guess ultimately what you're going to have to do is use one, in that problem on the written assignment, you're going to have to use one column operation in order to get rid of a non-zero element in the upper right position. So maybe we'll look at that toward the end of class today to kind of see how you might do it. So is this okay so far? Any questions? LDU or LU factorization is often used for computational purposes. We're going to make use of it next week when we start thinking about vector spaces. So it's something to kind of keep in the back of your head that a non-singular matrix has this sort of decomposition. We're going to wind up talking a little bit more about LU factorization next week, though perhaps not in as much detail as this. So the next thing I think I'd want to talk about is inversion of matrices, matrix inverses. So let's see. Just like with LDU factorization, finding an inverse corresponds to something that we kind of already know about. So if you're looking for a matrix inverse, it turns out to correspond exactly to Gauss-Jordan elimination. A few things I'd like to say about it. it's reasonable at this particular point to say that the square matrix A is invertible exactly when there is a matrix B, which cancels it from any direction. It turns out that it's the same, if the matrix is square, AB equal to BA equal to the identity matrix. So it's sort of like saying, there are certain numbers which have multiplicative inverses. So if you take a number like 7, you can multiply 7 by 1/7 and get 1. That's the role that the inverse matrix is playing for a matrix. Now, it turns out that some matrices have inverses and others don't. In this set of slides, we'll look at an example, a 3x3 example, where the matrix does have an inverse. Matrices that are invertible are of full rank if you're dealing with a square matrix. What that means is that they have enough non-zero pivots. They're non-singular. So if you're in the 3x3 case, if the matrix is invertible, what you're expecting to find is that you have 3 non-zero pivots. You're completely able to row reduce the matrix. If the matrix is not invertible, what you're expecting to find is a 0 row when you work through row reduction. So, just again, matters of notation, we'll use the symbol a to the -1. This is sort of supposed to suggest you're dividing by a, but no one calls it that. To represent the two-sided inverse of the matrix. We'll look at some examples and then ultimately look at a formula, so to speak, for finding the inverse. So when people think about invertible matrices, just think about numbers. It's probably best to think about this just with an analogy. If you have a non-zero number, you can divide by it. If you have a matrix which is non-singular, you can divide by it too. It's just that the division looks weird. Is this okay so far?
Honestly, oh, sorry.
Yeah.
I'm still kind of a bit confused on, I guess, the purpose of Ldu factorization.
So when you're thinking about Lu factorization, we will see it again next week when we start talking about vector spaces. That's one reason we want to have it is because I guess what I want to say is that we want to use matrices to develop some important vector subspaces of Rn, and somehow Lu factorization or being able to decompose a non-singular matrix in this way is useful for having that discussion. So that's the theoretical reason why we want it. So I guess you'll have to delay that discussion. Think about we'll bring it up again sometime over the next 2 weeks when we start talking about the full theory of how you solve equations. But a practical reason why Lu factorization winds up being important is that from the point of view of computation, most computer algebra systems, when they solve equations, are going to use something like this. So matrix factorization is what tends to be used when you solve equations. It also is used if you've ever done any statistics or anything like this. LDU is not used for what I'm about to describe, but a certain type of matrix factorization is. So if you've ever messed around with stuff like least squares approximation, that's related to something called the SDD decomposition of a matrix. So when and the reason is that the sort of algorithms that you're talking about when you encode them as matrices are more legible if you have to put them into a computer. So that's another practical reason why maybe it's important to know Lu decomposition. But we're not really going to be coding these things into a computer. If you use computer algebra systems like Mathematica, it can solve equations very quickly, but it's using something like Lu decomposition to do this. If you get Mathematica to come up with least squares, it's using some other decomposition of a matrix to do this, as it turns out. And a lot of matrix decomposition tends to be associated with things that you compute. Does that make sense? I mean, that's why it's important.
I think so.
But these sorts of decompositions will be important to us, not for computational reasons, over the next couple of weeks. They're going to be important for us because it's easier to decompose or to discuss vector subspaces of interest if we know how to matrix decompose this, as it turns out. But that's a story we're going to have to get to.
So this decomposition is just like a unique solution?
It is actually, yeah. And so there's a theorem, and I didn't put it on the screen, but you're absolutely right. If you have a non-singular matrix of the sort that we dealt with in the example, its LDU composition is unique. So there's only one way to LDU decompose or factor a matrix. The sort of matrices that we're talking about. So it's sort of at the end of the slides. So yeah, it's unique. There's only one way to get an LDU decomposition for a given matrix if that matrix is non-singular. And of course, also if you don't have to flip any of the rows at any particular time. So if you're thinking about this by analogy, it's like if you take a number like 20, its prime factorization, right? There aren't two ways of factoring a number. It's similar to that. Does that make sense?
In a sense, yeah. I think it's going to take time to just like understand.
Yeah. Right. So when we think about inverses, invertibility or finding a formula for an inverse for us turns out to be exactly equivalent to Gauss-Jordan elimination. Gauss-Jordan, remember, is the algorithm that takes a matrix and produces the reduced row echelon form of that matrix. If you keep track, so the summary of the slides, I guess, is this. If you keep track of what row operations you need in order to row reduce the matrix, by writing down the elementary matrices necessary to carry out the row reduction, you're basically going to get a formula for the inverse by doing that. So I'd like to just talk a little bit in some rough sense about how that works. These are a couple of facts. One thing that if A and B are invertible, I guess I should say this before I get down, to add the actual calculation. But if A and B have inverses, if they're invertible square matrices, if there is such a thing as A inverse and B inverse, then the product is invertible. So A times B also has an inverse. More than that, the formula for the inverse is just the factors AB written in reverse order. So basically it's B inverse times A inverse, if that makes sense. You can check that directly. If you take A times B and multiply it by this thing right here, the B's in the middle cancel to the identity matrix. So I guess what I would say here is that B inverse is the identity. And remember, the identity matrix times anything is that thing. So when you produce an identity matrix here, it's a bit like producing the number 1 in a factorization of numbers. It doesn't change the product. And so this product right here is in reality A times A inverse, which is the identity. So that turns out to be something you probably should remember. The formula for the inverse of a product, AB, is just B inverse times A inverse. You can check it directly just by multiplying these things together and remembering that matrix multiplication is associative. That doesn't really tell you much about how to compute the inverse, but it's a fact that's worth remembering because we'll see it again. So let's get around to the actual computation. Suppose that A is a non-singular 3x3 matrix. If it's non-singular, we know that there are a finite set of elementary row operations which will convert such a matrix into the identity matrix. This is basically the content of Gauss-Jordan elimination. What's an example of this? If you have a matrix A, it turns out that this matrix is indeed non-singular. It turns out, and I guess I say we should verify this, but I'm not going to, that's one thing that I might leave to you, that this product of elementary matrices that you're seeing here, this guy right here, when you multiply all of these guys times, so I wish I wouldn't have done that. When you multiply all of these guys times A, you wind up getting the identity matrix. So what you see here, the product of these elementary matrices is the inverse of A. So the product of these matrices here is A inverse. Why? Because when you multiply it by A, you get the identity matrix. So definitionally, that's got to be the inverse. So, how did you actually get these? You have to think it through. E21 comes from putting a 0 here. D2 makes this pivot, whatever it is, equal to 1. E12 and E32 eliminate those two positions respectively. D3 makes the third pivot equal to 1. E13 and E23 eliminate that and that pivot. So all those elementary matrices are doing is they're just recording the elementary row operations necessary to row reduce the matrix to the identity matrix. That's really the only role they play. So if you want to, you can sit down and write down by hand, you know, what the elementary row operations are that correspond to the left multiplication by these elementary matrices. But at this point, it's not really necessary to do that, because the fact that you have an elementary matrix which represents a row operation is at least somewhat believable to us at this point, because we've done the matrix multiplication. So that big product of elementary matrices, it turns out, is the inverse. Now, the question you have to ask yourself when someone presents you with this information is this information of any practical use? You know, if you actually wanted to compute the formula for the inverse, this would involve taking the product of all of these matrices, and that's a bit of a pain. You could do it, but that's 1, 2, 3, 4, 5, 6, 7 matrices. You could take the product of the 7 matrices. You could work out the formula for A inverse that way. You could do it. The reason I think that this is important is not from the point of view of any kind of practicality. A computer can multiply those matrices together pretty much instantaneously, and it's going to view a row reduction in this way. But a human, that's pretty intimidating to see a product of 7 matrices that you have to multiply together in order to get the inverse. So there must be a better way. So are there questions about this so far? Now, when you take a look at what's written on that previous slide, I'm not really writing down any formulas for matrices. It's only just notional. If you take a look at those elementary matrices, the idea is that if you really wanted to know what the inverse was, you could write down formulas for each of those things based on what the various pivots were, based on what the various things are that you have to eliminate in the matrix. You could do it. I mean, I'm not saying that you should do it, but you could. It would probably take, 15, 20 minutes to sort of work out all the details. I'm not arguing we should do that right now. It might be something that's worth doing later. One thing I would point out is that there is a problem on web work a little bit like this, where you have to find a formula for various elementary matrices which are responsible for row reducing a matrix into the identity. I think it's fewer than 7. I think it's really only 4. But you just have to think through what those things are. Are there questions about this so far? What we have inside the set of parentheses, whatever that matrix is, it is the inverse of A. And this is because when you multiply that matrix times A, you get the identity matrix. It cancels A, but it's just this big product. It's a bit of a pain to try to work out. Are you with me up to this point?
Those are just elementary matrices, right?
You're absolutely right. Yeah, they are. And so the idea in Gauss-Jordan is that if you have a non-singular matrix, you can row reduce that matrix by left multiplication by elementary matrices. And each of those elementary matrices corresponds to a row operation that you would ordinarily carry out. Now, the good theoretical reason to have elementary matrices we're sort of seeing, you can come up with at least an abstract formula for something that's invertible. It's telling you, what that formula is telling you is that if a matrix is not singular, then there is an inverse. So if you're thinking about matrices or you're thinking about systems of equations or anything like that, that's useful information. It's telling you that if you have a matrix and you row reduce that matrix and you get ones along the diagonal, then you know that guy has an inverse. That's one way of looking at it. Not only that, you know the formula for the inverse, at least notionally. If you take a look at the elementary matrices that you see in that big product, if you were really to take the trouble to multiply all those things out, that is indeed the formula for the inverse. It's just kind of a pain to carry out 7 different matrix multiplications. A computer could do it very quickly, but we're not computers.
For clarification, you're saying that it's invertible if you row reduce and you get the identity matrix.
That's right. if you have a 3 by 3 matrix or an n by n matrix, if you carry out Gauss-Jordan elimination, and if you wind up with ones along the diagonal and zeros everywhere else, it turns out that that matrix is invertible. That is because Gauss-Jordan elimination is equivalent to finding a formula for the inverse in the way that's on that slide. Each row operation that you carry out corresponds to multiplication by an elementary matrix on the left. And so basically, if you carry out successive row operations, which eventually row reduce the matrix to a matrix of ones along the diagonal, zeros everywhere else, you've effectively found the formula for the inverse. If you just sort of keep track of what elementary matrix is doing the job. So all you would really have to do is multiply the elementary matrices together to find the inverse. But you know, if you have a big matrix, that's a intimidating kind of thing to do. I guess it might take time. On the other hand, if you have a square matrix, suppose you were to row reduce it and you wind up with like a row of zeros or something like this. If you wind up with a row of zeros, that matrix is not invertible, not invertible. There's no formula for an inverse in that case. You would wind up with a zero pivot. You know, stuff would break down. So is this okay? Good. I'd like to be able to kind of talk about how you practically come up with the inverse. And, you know, with a lot of these things, you know, in classes like this, you generally are going to be able to find the inverse by hand. I don't want the matrices to be too big, because that becomes kind of a pain, particularly in this day and age where computers will find formulas for inverse much faster than we can. But I do at least think it's important to explain where or how they're doing that, and it's generally going to come from something like this. So factorization into elementary matrices tends to be the way that you want to look at the problem. That's a more theoretically productive point of view, but at some point you just have to calculate the formula for the inverse, and we'll do that presently. So it's a bit of a pain. You know, talking a little bit more about this, notice that each of these elementary matrices has an inverse, and the inverse of the matrix is of the same type. We can get a factorization of A also as the product of elementary matrices. You know, so that formula is telling you, you know, quite a bit more than you think. So that first point is more important than you might guess. When you think about numbers like 64, 100, 125, you know, you're accustomed to the notion of thinking about factorizations of numbers into prime factors. You think that factorizations of numbers into prime factors is unique. The order in which you write down those prime factors is unimportant, because multiplication of numbers is commutative. You know, and of course all that's true. When you're thinking about matrices that are non-singular, we're kind of achieving the same thing with the sort of equation that you saw on that previous slide. If you think about the equation, all those elementary matrices times A equal to the identity, indirectly, that gives you a formula for the factorization of A. All you have to do is sort of invert those elementary matrices one at a time. So those elementary matrices all have inverses. We've already talked about the E sub ij. You know, things like D have an inverse, but it is what you think it is. Remember the matrix D, you're sort of putting a number, you basically have an identity matrix except at one spot. And in that spot, you put a number that you want to multiply by. So its inverse is 1 over that number, and so on. So all of those elementary matrices all have inverses. So when you're thinking about, you know, when you're thinking about that formula, it's a pretty powerful formula. You basically have a way of talking about not only a formula for the inverse, but a formula for A. And so, you know, if you view, you know, if you view this as by analogy with trying to understand how prime factorization of numbers work, it's almost as though we're taking non-singular matrices and we're writing down the prime factors of what those matrices look like. We don't get quite the freedom we do with numbers, because matrix multiplication is not commutative. So you really would have to wonder if the factorization of A is unique into these prime factors. There's a little bit to say about that. You know, probably we won't get quite to that level in this class, you know, when we start talking about what happens when you commute matrices, but it's an important question. I mean, I'm not saying you shouldn't ask that. If you take AB and BA, you know, what's the relationship between these two products? There's a question on the there's a question on the written assignment about that sort of thing in the 2x2 case, which I'll probably wind up talking a little bit about at the end of the day when there's time. So are there questions about this? Is it good? I mean, it's just theoretical, you know, you can write down a formula for the inverse in terms of elementary matrices. Okay, that's great. So, you know, if you notice that the matrix is non-singular, you can come up with a formula for the inverse. If the matrix is non-singular, then it's invertible. Converse turns out to also be true. If the square matrix is invertible, then it's non-singular. So invertibility and, you know, non-singular wind up being exactly the same quality. There's no difference between them. I'd like to talk maybe a little more in detail about how you calculate the inverse. A somewhat easier approach to the calculation of the inverse is to think about how matrix multiplication works. So instead of thinking about elementary matrices, you know, as we did in the previous slide, more practically, if you actually wanted to compute the formula for the inverse, if this is A right here, and if this is B right here, you're looking for a B matrix, which when multiplied on the right, when you multiply A on the right by it, you get the identity matrix here. And so remember that matrix product has the matrix product like this has columns which are linear combinations of the columns in the first factor. That's this guy right here, weighted by the appropriate column in the second factor. So we're basically solving for what these columns are over here on the right. That's sort of the point of that last, that's the point of the last statement. At least we'll see that in just a second. So let's see. So what does that mean? So the first column of the identity matrix you can write as 1, 0, 0. If you remember that matrix multiplication, has column, you know, the product has columns which are linear combinations of the columns of A weighted by the columns of B, you're going to see that the first column, we want to solve for coefficients B11, B21, and so on. We want to write the columns of A as a linear combination which adds up to that matrix. And if we can find coefficients here, here, and here that do that, then it's possible to at least find the first column of B. The same thing is true for the second and third columns of B. We want to be able to find 0, 1, 0 as a linear combination of the columns of A. We want to be able to find 0, 0, 1 as a linear combination of the columns of A. And by doing that, we are finding a formula for the columns of B. And so that's sort of what motivates what we're about to do next. If you want to solve those three equations, there's no particular reason why you would not put everything into a big augmented matrix and solve them simultaneously. So what I mean by that, so, you know, if you wanted just to figure out, I guess so this slide's sort of intermediary. If you wanted just to figure out what the first column of the inverse was, what you have to be able to do is solve this system of equations. You would usually take the matrix form of the equation and write things down in an augmented matrix. When you row reduce this, you're going to be able to come up with B11, B21, and B31 in the way that you think. But if you can do that for one of the columns, why not do it for all of the columns at the same time? And that's generally what this means right here. So when you take this large augmented matrix, what's going to happen as you row reduce the left-hand side, as you use Gauss-Jordan, what will appear over here in that column and that column and that column is a formula for the inverse. Because if this is reduced to Gauss-Jordan, we're going to be able to solve for the columns directly, because remember, you know, we would just have to remember that these columns are associated to different sets of variables depending upon the column we're looking at. But what's going to happen is that when we row reduce this, the columns that you see here will be the columns of the inverse. When this piece, so I'll draw a line right here, when this piece right here is ultimately in reduced row echelon form. So from a practical point of view, without trying to keep track of an endless number of elementary matrices, which you then have to multiply, all you really have to do, because of the way that matrix multiplication works, because of the way that solving equations works. You just have to row reduce a matrix, and you can determine, and this will determine what the columns of B look like. What I'd like to do, maybe in the next few minutes, is just to have people do this by hand. So here you have this matrix. So it's an exercise. So remember, this piece right here is A. Find A inverse by row reducing the matrix. And by that, I mean, put the reduced row echelon form here and see what happens over here. What will happen is that the resulting columns, when you do this, will be the columns of the inverse matrix. Then we can verify that, I guess, by hand. So right now it's about 10:21. My guess is that it would probably take about 9 minutes to do this exercise. So take a few minutes to do it. Right now, let's meet again at maybe 10:30. We'll see what people got, or at least at least I will carry out the reduction. We can see if it's similar to what you got. And then, we'll talk a little about the written assignment 1.
So are we supposed to reduce the augmented matrix as well?
Oh, yes.
Okay, so we'll reduce the entire row.
Yes, that's right. Yeah, so what you're trying to do is you're trying to make A look like the identity matrix. And as this happens, what's going to happen in these columns is that you will see the columns of the inverse appear. You're basically solving 3 different equations simultaneously. And they're these 3 equations. So basically the goal is to try to find these coefficients B, which make the columns of A linear combinations, which add up to the rows of the columns of the identity matrix. If you can find these entries B that do this, then you basically have found the inverse. But to be able to find those entries B, it's the same thing as being able to solve equations which look like this for each column of B. So this is just the first column, right? So this is the augmented matrix that you would be worried about if you just wanted to know what the first column of B was. You would figure out what the first column of B was by doing that. If you wanted to know by row reducing this and finding a formula for the B's. If you wanted to know what the second column, what's the first column? If you wanted to know what the second column of the inverse was, you would solve this system of equations. Because again, solving systems of equations is equivalent to finding linear combinations of the columns of A. So whatever you get whatever you get out of this will be the second column, whatever you get, I guess, ultimately out of this will be the second column of B, if that makes sense. To find the third column, it's the same thing, except the solution column is 0, 0, 1. But I guess the point is that instead of just sort of rewriting this and doing it 3 different times, you can just do it all at once. Does that make sense?
Yeah, that makes sense.
And so, basically, so finding the B's amounts to solving equations. And so there are 3 systems to solve, but why not just do it at once? So if you do it all at once, what will show up on the right-hand side are the columns of the identity, are the columns of the inverse matrix. So that's the goal. So right now it's about 10:24. Let's take a few minutes. Let's take about 8, 9 minutes to do it. We'll meet again a little bit after 10:30, maybe 10:33. I'll work out what the inverse is, and then this will give us a few minutes to talk about the written assignment as well. All right, so we're back. So, hopefully you row reduce the matrix, and you can kind of see the formula. You can see the formula for the inverse. Let's do that real quick. And then we can talk a little bit about the written assignment. Oops. Okay, so let's see. Right. So if this is the matrix A, remember that the goal is to essentially solve 3 independent sets of equations one at a time. But you could do that. But the advantage of this particular method is you can kind of solve all the equations at the same time. So there's no need to just sort of re-replicate the row reduction, which is essentially the same, whether or not you're looking at 1, 0, 0, 0, 1, 0, or 0, 0, 1 in the solution column. So if you start, let's see, 1, -1, 2. So I have to remember what the matrix is. So I'll write it down. 3, 2, 4. - 0, 1, -2, or 0, 1, 2. And we're representing the situation as representing what we have to do is this big augmented matrix where we're basically trying to solve. So I'll put the line here to indicate that it really is augmented, just to remember that that's there. And my solution columns are all over here. Now, I'm lucky in this situation that in the first pivot, you have a 1 and you have a 0 down here. So that makes much less work to do. I want to be able to eliminate the 3. So if I'm keeping track of the row operations, what I would do is I would take row 2 plus -3 row 1, and I would replace row 2 with that. But remember, I'm going to have to do this across the entire matrix. Oops. There's my row 1. Of course, you get a 0 here. 0 is already there. If you take a negative 3 times -1, that's going to be 3. 3 and 2 is 5. 3 times 2 is -6. -6 and 4 is -2. You take -3 times this 1, add it to the 0. That's a -3. You get zeros here, so that shouldn't change. And then there's really not much to do with the last row. So normally, if you're in the situation where you have a non-zero number right there, you might have to have one more elementary row operation, which is supposed to get rid of that number. But in this case, we don't have to worry about that because there's a 0. If you're keeping track via multiplication by elementary matrices, we have just multiplied that augmented matrix by E21. And E21 in this case would be equal to 1, 0, 0, -3, 1, 0, 0, 0, 1. It just depends on your point of view. The next thing that I would do if I'm approaching this from the point of if I'm undertaking Gauss-Jordan elimination is to take a look at my second pivot right here. That's a 5. I want to produce a 1 there. And so what I do is I take 1/5 row 2 and I replace row 2 with that. So you get 1, -1, 2, 1, 0, 0. Last row, not much happens. The middle row, the second row, that's a 0. That's a 1 by design. You get a -2/5 here. You get a -3/5 right here, and you get a 1/5 right here, and the 0 right there. And so if you're keeping track with elementary matrices, if you're keeping track of what you're doing, that's a D2. That looks like 1, 0, 0, 0, 1/5, 0, 0, 0, 1. So, we have 2 elementary matrices. If you really wanted a formula for the inverse in terms of its factors, that's the only reason I'm really writing those down. But, in effect, the procedure of solving equations will be able to produce an inverse anyway. So is everyone with me so far? Is this all right? You got this so far?
Yeah.
Okay, so we'll go back. And so you just sort of continue to do this. The second pivot is 1. It's right here. You want to be able to cancel that and that. So I'll write these things down together. We take row 1 plus row 2, and that goes into row 1. If you're keeping track of this with elementary matrices, that's an E, let's say I want to bit, what is that, E12? And so I get something like 1, 1, 0, 0, 1, 0, 0, 0, 1. I also need to eliminate the 1 in that position. So in order to do that, I take R3 plus or minus R2. I replace R3 with that. For that position, I need to have, I guess, what is it? An E32. And that should work out to be 1, 0, 0, 0, 1, 0, 0, minus 1, 0 in this case. If you carry out the elementary operations, of course, you wind up with a 1, 0. When you add in the first row, when you add up -2/5 and 2, 2, I guess, is equal to 10/5. So you get an 8/5 coming out of there. You need to also add these two things up into the first row that you see here. 1 and -3/5 combine into 2/5. 1/5 and 0 is 1/5. You get a 0 here. Second row is the same. Right? In the last row, you get a 0 here and a 0 here. In order to produce the last row, remember, I take the negative of row 2 and add that to row 3. So the negative of row 2, is, at least from the point of view of that particular spot, is 2/5. 2/5 and 2, 2 is 10/5. I think you should get 12/5 right here. You are adding the negative of that to the 0, so that's another 3/5. You're adding the negative of 1/5 to 0, that's a -1/5. You're adding 0 to 1, that's 1. So I guess this is a point in time that I would probably usually stop. I'll continue to write down the next few steps, but they're probably evident to you to find the inverse. The next thing you do is you would create a 1 right here. And so you would replace row 3 with 5/12 row 3. That would have the effect of making that into a 1. And then you would eliminate the positions above the third pivot. And so in order to do that, you would take row 2, and that 2/5 is not going to change. So you would take row 2 plus 2/5 row 3, that would go into row 2. To eliminate the 8/5 that you see there, which will be unchanged by the action of multiplying that last row by 5/12, you would take row 1 minus, or rather plus -8/5 row 3, place that with row 1. And after you do those things, you're done. And so what would happen after you've done all those things, those last two steps basically amount to figuring out what that last column is. You're sort of in the position where you would have an inverse showing up on the right side of the equation. You would be able to read the formulas for the B's just by looking at the columns on the right. That's the formula for the inverse. On the other hand, if you're keeping track of all of these things through elementary matrices, the product of those elementary matrices would also be the inverse. So there are various things you can do at this point. You can check that the product is actually equal to the formula for the inverse that you have. Another nice sanity check, if you take the thing on the right-hand side that you get after you've completely row reduced the left-hand side of the augmented matrix, what should occur if you take the right side and multiply it by A, the original A, you should get the identity matrix out of it. That's because by design, after you've finished row reducing, the thing on the right side of the augmented matrix, it is supposed to be the inverse matrix to A. So, you wind up getting a formula for the inverse in this way, a couple of checks to make sure that it's reasonable. But I don't know that there's too much more to say than that. That's the practical way of doing it. But again, I don't want the class to sort of devolve into just this endless sequence of calculations of the values of augmented matrices. The important point, I think, here is that there is some kind of relationship between solving equations and the formulation of an inverse. So these things are related in some way. So that's the part that you shouldn't forget. You probably have to find an inverse once or twice just to convince yourself that you can do it. But beyond that, in reality, if you really have some big matrix, if you have like a 50 by 50 matrix, you're not going to sit down and work out what the inverse is using some kind of elementary row operations by hand. You're going to outsource the work to a computer. But this type of work is just meant to suggest that there's a relationship between multiplying by matrices, between finding formulas for inverses, and between elementary row operations and solving equations. Is this good so far? Okay. So with that in mind, there was one more set of slides to talk about. There's about 17 minutes left. We could probably do that, but to be honest, I think a better use of the time might be to talk a little bit about the written assignment. The last set of slides isn't totally necessary. We'll get back to some of the issues involving symmetric matrices at a later time. So what I'm going to do is bring up a copy of the written assignment, and we can talk about it a little bit. It's over. I'll have office hours as usual at 1 p.m. If I see you there, great. If not, then I will see you or hear from you over the weekend. And if not even that, then I'll probably see you next Tuesday.
Thank you.
Thank you.
Thank you.
Yep, take care.
Thank you.
Thank you, Professor.
Yeah.
I just want to ask again. Could you please update the put the notes on the canvas, because use the video to review is to not efficient.
So I think there are. So let me go to Canvas. The notes I thought I put up in a separate module. So I think the notes should be good. I think as of yesterday or today. So let me check.
Okay. So how could I?
Yeah. So if you're on the home page for the course, I think the first thing that you probably see is the various slides and homework assignments which are present. Right below that, I think you have the set of at least some sets of notes. So it's a set of notes. I think 628. It was just like one set of notes. Because I don't think I did stuff as systematically on day one anyway. So the set of notes that I have, I think on 629 and 630 are up there, and they're labeled by date. Of course, the notes from today aren't there, because I've annotated them. But the notes themselves are right below the stuff that has the weekly assignments.
Oh, let me check.